Rob Monto from the Army Rapid Capabilities Office. Just a little background. A little over 2 years, this office has stood up to address strategic needs for the Army. And one of them is in the electronic space. And we want to get at applying some AI or machine learning into this domain. So we thought about some novel approaches and had a great team here to kind of kick it off. So what we're going to look at today is kind of what the process was, some observations, some results, and really and just get some of that feedback from the community. First foray into here and looking to see where we go next. But overall, kick it over to Bill, Mr. Bill Urego from MITRE. Thanks.
Thanks, Rob. Yeah, so my name is Bill Urego. I'm a chief engineer at the MITRE Corporation. I was the principal investigator for this task for the Army RCO. Before I get started, so a couple of weeks is my daughter's 4-year-old birthday. And last year, I got her first set of walkie-talkies, Minnie Mouse walkie-talkies. And she had a hard time with the concept that in order for me to hear her, she had to actually push the button. She just wanted to talk into it. And I'd hear her in the closet just kind of talking away to herself. After I kind of taught her, you got to hit the button, it was again, well, you got to let go of the button if you want to be able to hear me. And we're working on that. But I thought a good idea was, well, why don't I hook up my USRP, put her in front of GNU Radio, and it's not the first time I've put her in front of GNU Radio Companion, and show her the correlation that when you push the button, there will be a nice little blob on the waterfall plot, and some energy will be displayed, and she'll get it. She'll get that when she hits that button, something happens, and that actually helped her, at the age of 4. So there's some cognitive ability that I think was interesting. Now, there was other things. I was just displaying wideband spectrum when this thing popped up, so there's other signals in that spectrum, and she goes, "Daddy, what's that?" And I kind of looked and I go, I don't know what that is, right? But that's what I do for my job every day, Kayla. So hopefully when you're older, you'll be interested and keep asking that question. And so some of the motivation here that we find in this community is a lot of times the systems that we work on, we are the unintended receiver. We are in an environment that we really know not a whole lot about. There are a bunch of signals in that space that we kind of want to understand. So the first question is, what's really important to me? What am I looking for? Where do I tune? How long do I sit there? What do I process? What do I want to actually try and pull out of the environment and flag as anomaly or something of attention? And how do I bring that to the attention of other systems in that environment? So this is why I think we were really interested in novel processing techniques, technologies, and we've been paying a lot of attention to where the computer vision world has gone since 2012, what's being done in natural language processing, and just the explosion of various different deep learning technologies that is kind of putting the data first and allowing these deep neural networks to pull out and extract features and kind of run with them for inference and other things. And so the motivation of this challenge was, the RF world, the EU world, EEs, we've been focused in machine learning, and there's been, in the past couple of years, a few efforts applying deep learning, but as a community, we're probably 10 years behind where the computer vision community is. And we're trying to leverage some of those techniques, so what can we do as an organization to inspire some of that? What can we do to kind of get some data out there and have some people play with it, and not the traditional partners of the government? Universities, academia, people that are just interested in the spare time, the GNU Radio community. And so that's one of the inspirations of this challenge, was to be able to put some information out there, put some data out there, put out a challenge and see what are the different approaches, what are people going to come up with. And we actually got a lot of participation that we were really excited to see. So the challenge was only a couple months. We only prepared for it for maybe 8 months. It started with generating a data set of 24 different modulations, generating various data sets, training and test data sets, and making a website available and putting all the resources on that website for participants to go and get the data, download the data, get some tools to be able to process the data, and then submit their results into a scoring system. And one of the things that I want to point out, the participation that we had, we had over 161 teams register, and 43 teams actually submit results to both test data sets. So we were able to get a lot of data back and start analyzing it. And the talk today is really to kind of share some of our insights and our observations with the community. One point is it was great to see the participation in the community wasn't from the traditional partners that we normally work with. It was, I mean, the majority were solo teams, individuals that just were interested, that were, you know, grad students, undergrad, hobbyists that just wanted to play in the competition. So last year at the GNU Radio Convention, Paul Tillman from the DARPA program briefed a similar chart to this, and this is kind of getting at the motivation of why we're interested, what are the application spaces that we're interested in applying these things to. So the bottom axis, we have the discrimination complexity. So if I'm looking at wideband spectrum, how many signals do I want to discriminate? How many do I want to classify? How many devices? You know, how many different types of things are out there that I'm really trying to observe in my observation space and make decisions on? And then on the left-hand side, we've kind of taken the Bloom's taxonomy of learning theory and relate it to cognitive complexity. So what are the types of questions that we're asking? So for example, if we are doing signal analysis today or signal forensics, you know, I may look at a signal, I may start to understand some of those external parameters or the features of that signal. I may write some algorithms to be able to detect on that signal and identify it and characterize it in all different kinds of ways. And I'm in this bin of, I do a really good job at knowing what's out there. And for new signals, it takes a little bit of time to figure out what they are and if they're important. So how do we start to break outside of that box and ask other questions? You know, for example, the ModRec problem. If I have a mechanism to just understand, you know, your symbol rate, your bandwidth, your center frequency, maybe the list of frequencies that you're using, your modulation, and I could see what different modulations that you're using, I could maybe kind of understand what you think of the channel environment. If you're going from a very high order modulation to a lower order modulation, I could start to understand maybe you're just not trying to send a lot of data, or maybe you believe the channel environment degraded a little bit. And that's something that I can now learn about your transmitter and receiver that I could use for other characterization and other information. That's where we were really trying to go with this first challenge, is putting out modulation data sets and seeing how people do with that. But where we kind of want to go was the other questions of, if I am looking at thousands of signals from DC to daylight, or if I'm looking at dozens of gigahertz of spectrum, I have this detection and localization problem. What's important? Where do I want to look? How do I want to look? How do I want to spend my resources? And so where we want to get to in the next year or so is continue these challenges and inspire the community to look at various different mechanisms to take the stuff out of the CV world and apply object detection and localization, whether it's using spectrograms or it's using raw IQ data. But it's almost the question of, how do I channelize? So I'm looking at a couple hundred megahertz of spectrum. So how do I want to channelize that spectrum and then go process signals in that? But the application areas, what we see in the community is there's a ton of focus on signal classification, whether it's automatic modulation recognition, or it's device fingerprinting, or protocol identification. And what we kind of like to see is that's one application area, that's one bucket. There's a lot of work in anomaly detection that we're excited about, including the previous speaker. But there's still pattern of life analysis. So I have these nodes that are out there that are communicators. Well, how are they organized, right? What networks are out there? How are they, you know, who's talking to who? Why are they talking? What are the critical nodes of that architecture? There's other areas such as signal synthesis. So the DeepSig guys gave a great talk about the work that they were doing with variational autoencoders. So I may want to design a system that is incorporating techniques to come up with adaptive ways to communicate that's really going down that cognitive radio route in ways that I haven't done before to adapt to the channel environment. And decision analysis. So if we want to automate the workflow of signal analysis, there's different areas in that where we may want to take the burden off of operators to say, here's kind of some of the things that you do next to help you characterize and understand the signals that you're seeing in the environment. So this is kind of a frame that we use to kind of put some context around a problem space. So a little bit of the work that we've been doing. So we were studying different approaches. So there was, out of the Virginia Tech Hume Center, there was a number of papers on applying convolutional neural networks to automatic modulation recognition. And we were interested in just what other types of approaches could solve this problem. One thing that hasn't really taken off in the community is using complex valued convolutional neural networks because of the challenges with implementing those. But the medical community has done some work in looking at MRIs, and we figured we'd take a stab at it as well. And we did a quick comparison of a complex valued neural network versus a real valued neural network. The main intuition there was if you actually have a complex valued neuron that's taking complex valued input and doing the convolution there, you can imagine all those inputs coming in where you want to capture kind of what's happening in the biological sense. That, does that neuron fire when all of its inputs are in phase or out of phase or some weird phase? And is that information content currently being captured in real value neural networks? Or did we actually save the phase information enough for that information to be utilized? The other hand of the side is Jeffrey Hinton a couple of years ago, or last year, published on capsule networks. And we decided we would also take a look and implement and train a bunch of capsule networks on the MODREC problem and compare that with traditional convolutional neural networks. And the most interesting thing out of this is we didn't get great performance out of it, and we didn't spend a lot of time optimizing it, but we decided, well, let's go ahead and ensemble these two technologies together. Ensembling neural networks has been kind of a talk on various different machine learning forums in the past couple of years that we said, why don't we try it as well? And let's see the performance that we got. And we actually got pretty decent performance out of that. And we show a couple of the confusion matrices, and I know it's a little bit hard to read, from higher SNRs at the top left going down to lower SNRs. And so this was a little bit of inspiration to say, this is going to take a lot of time to figure out what are the best approaches to some of these problems. And that this is kind of an undefined space right now. And that was, again, one of the motivations for this challenge, is we wanted to see a number of participants to try things that we haven't tried before and kind of learn from that. And so when we were looking at this stuff, we were also looking at how do we integrate these solutions into an actual system. And this is a nice pictogram of a process. As you know, the process is really kind of messy. But it starts out with just talking about what do we need to generate? What do we need to collect? What's our problem? And going into actually generating a lot of data. And we spent a lot of time generating data, terabytes upon terabytes of data. I think the one thing in our world is, we compare ourselves to the image recognition world, and they talk about big data. But I could fill a petabyte hard drive in a day by just collecting on a couple gigahertz of spectrum. The environment that we set up was originally, a bunch of GNU radio code to actually generate data. And we set up a lab environment so that we could synthesize this data right to a file, add different channel impairments, or put it over the air and receive it through other software-defined radios that we were working with within the Army, and actually generate massive amounts of data sets. And the problem with this stuff is, you hit a button, you develop these scripts, and you walk away on a weekend, and you come back, and the whole thing didn't work, right? There's mistakes that are made. I think one of the team members over here, he set it up where we were using a software programmable attenuator to just set different attenuation on the signal to collect at different SNRs. And the entire attenuator crapped out, on us over the weekend, and we lost 48 hours of data generation. But the nice thing about this entire software community is that 48 hours is, to hit a button and generate 5 terabytes of data is 2 overnight sessions. So we're no longer kind of data limited in this community, which is nice. But just having a ton of data, just having terabytes of collected data that is well annotated, doesn't mean that you necessarily have a data set. Right? To be able to take this data and actually train up various different machine learning or deep learning algorithms, there's kind of community conventions on how you do this. TensorFlow, for example, and the data API and TensorFlow records, you kind of have to build infrastructure around that to be able to get your data into your training sessions. So there's a lot of work that actually goes into, once you have the data? How do you organize the data? And I think this is where we've been putting our experts, right? Experts that have been doing the signal analysis, and instead of writing these algorithms, to actually go in and organizing the data and generating these data sets that can be used to develop these or train these different algorithms. And then finally, the training process. You know, there's a bunch of techniques, you know, that are in and out of popularity, and trying all these and seeing what's working well, or dynamic learning in your training process are all massively, you know, found in the literature. But again, what's the best techniques for us? Then once we have this model, if you actually want to get it to run in real time on a system and drop it in, you're now under the constraints of how are you getting that data off your radio, your IQ data that's coming in at, you know, a couple hundred megasamples per second into, right, this environment, where if you're using something like TensorFlow, you know, the ability to actually go and, you know, compile TensorFlow, you know, and their C API and get that running is actually not widely used. So you're kind of stuck in the Python space of, you know, usually spinning up a Docker container that is TensorFlow and managing the, you know, your memory allocation of IQ data and pre-processing it and putting it into your algorithms. And those were all a bunch of challenges to actually get this thing working in real time. And so when we were training up, you know, some of the neural networks like ResNet and AlexNet that are common in the ImageNet competition that have like 200, 500 million trainable parameters, and getting that to run with very little latency is very challenging and taking forever to train these things. So there was a lot of optimization on, you know, how do we reduce the complexity of these neural networks and get them to run in real time and give us real-time inference. And also using tools like TensorRT to optimize them, to quantize them down to something that can run efficiently. But that's kind of the motivation piece, right? These are all the things that, you know, our research programs that have been actively looking at these problems that kind of opened up the door to say, we're not going to solve this by ourselves, right? This is too big of a problem. There's too much of a research area. If you look at the literature and you see everything going on, I mean, even if you look at the GAN Zoo and you see how much attention and publications are on generative adversarial networks every day compared to 2 years ago, there's just no way that we're going to be able to explore the space by ourselves. And so the competition was a chance to kind of explore this space with a very large audience. We had, again, great participation, but kind of looking at the scoring, we've broken this up to look at the top left is the overall accuracies, the top 5 teams, test set 1, test set 2, and our final score for them. The bottom left is the top 5 scores over time. So you could see Team Platypus had, you know, was on top throughout the entire competition, and a bunch of people got really close to them. And then the top 5 by signal-to-noise ratio, test set 1 and test set 2. And in test set 2, we actually included SNR values that were not part of the training data set. So we're asking some questions. Well, this is data that you have not trained on before, that has a little bit of different channel conditions, and how well are you going to be able to classify against this data that has a little bit of different information on it. And then you could see the confusion matrices on the right side for, again, the top 5 aggregated with test set 1 and test set 2. And test set 2 has started to look actually really good accuracies across all the modulations that we provided. So this was some of the performance that we got out of it, which I think was great to see how all the teams were doing. The next step is, you know, what were the approaches that they took? If they all tried novel approaches or if they all stuck to convolutional neural networks, that's kind of the next phase of this venture, is to learn about that. But we did also add in things that the teams were not cognizant about. So just as we're concerned with supply chain integrities of hardware solutions or software solutions, now we're in this age where people are providing various different trained neural networks. And how do we start to manage the integrity of data? So we injected some bad training examples. And we kind of asked ourselves, how many of those 170 teams are actually going to notice that this training example isn't correct? How many have that DSP domain knowledge? How many are coming up from other domains and they completely miss it? And we collected statistics and information on our forums of how many people were actually saying, hey, this doesn't look right, versus how many people just kind of ran with it. One of the things that we were plotting, which is the left-hand side, this is a confusion matrix showing the misclassification accuracies. And what we see here is there's a significant, and this was for test set 1, a significant number of the submissions, all submissions from every day and all teams were actually misclassifying or really getting confused on pi over 4 QPSK, and it was impacting 5 different classes. Essentially, they were predicting pi 4 QPSK as 8 PSK or 16 PSK, and offset QPSK and QPSK as pi 4 over QPSK. And the main reason that is we intentionally kind of messed with pi 4 QPSK to see what impact it would have against the overall classification accuracy. On the right side, we also included things in the data set and the test set that the teams were unaware about. This was our first chance. We had 43 independent solutions to solving modulation recognition on this data. And we wanted to experiment with a bunch of adversarial techniques to see if we could trick all those solutions. So we developed a novel co-channel interference technique, and we actually embedded a number of those test examples in the test set. And what we saw was the desired effect that we wanted. It was causing misclassification to the degree that we wanted them to be actually wanted them to misclassify to the certain examples that we had put in there. So all top 5 performers actually dropped in about 40% accuracy based on our co-channel interferer that we developed. And this is, again, a novel thing that we're further looking at and kind of diving into. But just to kind of wrap up, so these were the final scores, and we wanted to say thank you for your participation. It was great to actually get this much attention and see all the engagements from universities, people that were interested, the entire community. And again, congratulations to the winners, Platypus Aerospace, Team AU, and Thundering Panda. And we're looking forward to actually opening up engagements and conversations on your solutions and talking further with you. And also, now that we've kind of gone through this vetting process, for other government organizations, we have a lot more data available about what we analyze in the competition, and we have other data sets that we could provide you. So we're interested in that further engagement. And I guess to close out.
No, I think you hit it all, Bill. The only thing that I thought was interesting is how close the teams were overall on the accuracy, and just really that the first instance of us getting into this challenge is those are better than a guess, and that'll just help out with users in the field. So, and get off the stage slide here is just contact and follow us and whatnot for the Army RCL. But thanks for having us.
Okay, thank you very much. We have time for questions. Raj being first. Yeah, did you mind handing off your handheld? Okay, great. Who? Okay.
Hi there. I think this is for the RCO representative. What's the future of the data set that was released? I know that when you signed up for the challenge, you had to sign some data usage agreement. So what's going to happen with the 30 gig data set that you guys have already released? Thank you.
So right now, that's where the data set is. I think overall, we may be looking to expand that, adding different types of. Thanks, appreciate it. Just overall, I think we'll be looking to expand that. Right now, it's the 24 modulations. We'll probably be looking to eventually do different types of taxonomy, types of classes in there. But right now, we're just going to be at those 24 modulations. So
what I'm asking is for this, if everybody in the room wanted to download it today,
Raj, can you, sorry, I didn't realize this is annoying.
If he was asking if folks in this room wanted to download that data set, would they be able to? I don't think it's up on the website anymore.
No. So the
Yeah,
answer, the answer is no. We are looking at providing a sanitized data set, but we also acknowledge that the community is kind of moving forward by itself, right? So deep to the outset, they have a data set that we're releasing, and I think it's great that the community is providing data sets for the continuing learning. I think through other challenges, there will be other data sets, and we've looked at the broader distribution of those data sets, and there are challenges for us to actually let that happen.
Okay, questions over here. Can Rob go get mic'd?
Hi, so I actually downloaded your data set and then looked at modulations, and when I saw that OQPSK was not OQPSK, I asked a question about it, was told no information, and then dropped it because it looked like you guys were just incorrect. Are you guys saying that you did that on purpose?
There were some that we did on purpose. The offset QPSK one was not done on purpose. That was a mistake. It was a good thing we were consistent with our mistakes. During the challenge, we, again, our goal was not to get, the mod-rec solution that we could drop into systems, right? So we were looking at other aspects that I mentioned during the talk, and I think, when we saw the comments on the board, it was indication of other things that, yes, there are the traditional experts in this field that are noticing things that, is going to be a question of data integrity when the government starts looking at other solutions and can ask the questions of where did the data come from, how did they validate it, in what ways did they validate it. So I think those are highlighting kind of in this new field, new concerns that really haven't been thought about in the acquisition of these types of technologies.
All right, and related to that, there are other data sets available for doing single carrier mod-rec.
Yeah.
Your data set it was basically aligned already. You had a slide that had something about transmitting over the air and receiving on Army radios, but it looked like this was all synthetically generated. It was aligned. You could just plot the constellation and see BPSK and QPSK. Is there some reason you decided to make your own data set and then get modulations incorrect?
So there are. I think the first thing is the data sets that are actually not what we released, that were sent over the air, that was received through different SDRs. That was something used for various different projects. But it was that same infrastructure that was leveraged to kind of initially generate this synthetic data set. The primary reason for kind of keeping it simple, right, just these modulations, a little bit of white Gaussian noise, was to kind of just open up the aperture to people that aren't domain experts in electrical engineering and know anything about IQ data. I think the majority of questions that we got, not on the boards, but through emails, were really just trying to understand what is IQ data? What does the format of this data really mean? How do I treat these instances? Do I really treat them as 2 by 1024 instances, or do I look at 2 by 1024 by n instances that you provided as contiguous sampling? So there was a number of, I think, educational lessons and engagements with the community just in the whole process, and that was, I think, something that was beneficial.
All right, and then you also had some slides talking about a system that you were getting running real time. Can you discuss what that was? What was the system doing, and what data was it running on, and what is real time there?
Unfortunately, I will not be able to discuss that. But if you are working with a government entity and you want to reach out to Army RCO, we'd be happy to have those conversations.
Hello? Hello?
Oh, hi.
Yeah, thank you very much. So a couple of questions. First is, do you have further plans and other challenges or open source projects, either an RCO or some other related organization that you're aware of? The second question is a little bit technical. So when you collected the data, is this continuous streaming and then essentially just chopped up? Or?
Yes.
Okay.
Yeah. So the way that well, I'll let Rob answer the first question, but just to continue on the second question, the way the data was generated and collected, we would have a continuous wave going of that certain modulation. We'd add different channel impairments. We'd have a large file of contiguous samples, and then we would kind of randomly select from that file, different points at different, 10, 24, or whatever end samples.
And as far as future challenges, yeah, absolutely. Don't have them exactly lined up right now, but just follow us, check the website, join the mailing list, etc.
So we are already a little bit over time, but we have 2 other people, 3, 4. Okay, we have 4 other people. So, all right, we'll go
Sure. I was going to ask about future challenges too, but also, did you guys in parallel develop your own models to try out, to see what kind of performance you would get? How did that compare to what you observed?
We did. There was a number of efforts. I think I'll reserve how we did. I think it was interesting to see the performance differences between the two. We actually had a number of interns and other projects that we placed under the same rules and guidance of the RCO to develop their model, train it, go through our testing, see how they would do. And a lot of them did very well. They would have placed in the top 5. But they were using, they tried a number of techniques, right? So a lot of them tried convolutional neural networks. Some of them tried capsule neural networks. And there was one guy that used a different data set to actually try various different LSTMs. They all fairly did well, but they were all really big models, right? 300 million trainable parameters. And so it's kind of a trade space of we never bothered kind of looking at implementing them into the actual, a real system.
All right, so I'll do here, and then Juha, and then we're going to cut it off.
Hey there, Kyle Logue from Team Platypus Aerospace. We would like to say we really enjoyed the competition. We were, I guess, we looked at all the data when it first came in. We sort of did some hand inspection. We found some irregularities in OQPSK, Pi/4QPSK, FSK, some other oddities. I guess my question is, if the Pi/4QPSK was, purposely misgenerated, why did you guys sort of stop scoring it halfway through? Because we felt like that actually compromised one of our advantages that we had. Sort of, we saw a lot of teams catch up after that announcement.
Yeah. Well, we saw the impact that it was really having, right? I think the hypothesis was that it's going to have an impact, and it should only impact that class and maybe 2 others around it. We saw the impact that it was happening, to 5 or 6 different classes. And in our own studies, we had noticed when you have 2 modulations that have very similar symbol states and very similar symbol transitions, when you're training the network, those convolutional kernels, right, they take a lot longer to train. It takes more of them, and it kind of artificially requires you to have a lot more of a complex network than if you're dealing with modulation schemas that are very different. So we thought it was really fair to kind of in test set 2 not score that anymore, just because of the impact that it was having really across 5, 6 different classes. And that was not something that we really wanted, that we really intended it would have that broad of an impact.
All right, I'm afraid we have to cut it off there. Thank you very much.
Yep, thanks.